Hello everyone, my name is Mr. Los. I'm here to talk to you about everyone's favorite subject, stoichiometry, but we're going to combine it with some of the concepts of molarity that we've been learning more recently. And this is important because now we're going to deal with stoichiometry involving solutions, and really, when you do chemical reactions, almost always at least one of the substances, if not both, is a solution. So this is really something that's very important in chemistry, especially if you go on to take further chemistry classes like chemistry in college or AP chemistry or anything like that. So you're going to find that the stoichiometry concepts themselves are very similar, and all the core concepts are the same. So if you were fairly solid in stoichiometry, this shouldn't be too much harder. In fact, in some ways it's easier. In some ways it's less work. So you actually might find that it actually works a little more smoothly for you. But here's the big concept that we need to try to wrap our head around. Here's the most important thing about making solutions. Like all of stoichiometry, moles are important, and knowing moles and knowing the mole ratio and that kind of stuff. When we were doing regular stoichiometry, we were dealing with pure substances that we could weigh and change the moles and so on. But when you make a solution out of something, what you end up doing is you add a bunch of water to it. And so this cobalt chloride here probably wouldn't even undergo a chemical reaction in its powdered form like that. We'd probably have to turn it into a solution to get it to react. But once we turn it into a solution, weighing it is not helpful anymore. Because if you think about it, if you're going to weigh this solution, really you're just weighing a bunch of water. So we have to find moles in a different way. But once we find moles in that different way, the stoichiometry is going to proceed exactly the same as it did before. So depending on what class you're in, I know my students were given a workbook. They have this page in it. Page number might vary slightly depending on how it's being made available to you. But this is the page that I want to work on. And it talks a little bit or provides a little bit of a context and a thought process that you want to go to when you're solving these kind of problems. So it's important to pay attention to state symbols. It's important to read the question carefully and make sure that you understand what's going on. It's important to pay attention to things that are solutions and when we're being given volumes and concentrations, because that's going to be our tip-off that we're going to have to do the stoichiometry a little bit differently. So it says, suppose 100 milliliters of 1.5 molar HCl solution. So that's an aqueous solution right there, is added to excess magnesium, so we don't need to worry about the limiting reagents. How many moles of hydrogen gas will we produce, and how many grams? So compared to a normal stoichiometry problem, the only part that's going to change is the very part at the beginning that we're going to do this a little bit differently. This is a solution. So if you find yourself dealing with a solution, don't even look at the periodic table and start adding up molar masses. That's not going to help us in this context. This HCl is mainly water. What is going to help us, like I said, like in all types of stoichiometry, we need to get moles. And forgive my writing here, I'm trying to write on this vertical space, and it's a little bit challenging. What is going to help us is the molarity formula, because the molarity formula we can solve for moles. I'm going to pop in that concentration right there. So it's a 1.5 molar solution. I'm going to solve for moles of HCl. And then it's also really important to pay attention to the milliliters to liters conversion. This equation requires liters. The milliliters to liters conversion, you're going to do a bunch in this unit. It's moving the decimal 3 spots. In this case, milliliters to liters, we're moving it 3 spots to the left. So 100 milliliters, if we move that 3 to the left, we're dividing it by 1,000, is 0.100 liter. So hopefully that's a unit conversion that I think you'll get used to and be able to do really quickly if you haven't already. So instead of using molar masses and looking up at the periodic table, like I said, to find moles, we're going to do a bit of algebra here to find moles. To solve for moles, my unknown here, I'm going to multiply both sides by 0.1. And then what I have learned by that is in that solution, I have 1.5 times 0.1 is 1.5, I should say 0.15 moles of HCl. So I've determined the moles of HCl, and then from this point forward, this is going to proceed like any other stoichiometry problem that we have ever done in the past. The next thing that you always think about in stoichiometry is the mole ratio. So I'm being given a moles of HCl, or I've just determined a moles of HCl. I'm going to, from there, go to moles of hydrogen. There's many ways that we could think about this, but if we want to take a dimensional analysis approach, remember when we're doing the mole ratio step, we're always going to use the coefficients in the balanced equation, and follow the what goes up must come down rule. I like to attach to the mole unit the thing that I'm talking about. And so since moles of HCl is on top, it's going to be on the bottom in the next one. There's 2 moles of HCl for every 1 mole of hydrogen. So basically it's 1.5 divided by 2, which is 0.075. So I've actually answered the first question. It asked me how many moles of hydrogen gas we produced. Well, we had 0.15 moles of HCl, and then the mole ratio is 2 to 1, so that's half as many moles of hydrogen. It's 0.075. And then it goes ahead and asks me for grams. So again, like in any type of stoichiometry, once we have moles, we can always change to grams. This time I'm going to look at the periodic table, look at hydrogen's mass, and remember I'm going to add up 2 hydrogens because that's that coefficient 2 there. I like to go 2 digits past the decimal. So the molar mass of hydrogen is 2.02 grams. And that is the mass of 1 mole, so that's going to go down there on the bottom. So for every 1 mole of hydrogen, we have a mass of 2.02 grams. So just a normal mole to gram conversion like we've been doing since early in the year. So 1.5 times 2.02, it's 0.15 grams. Now, if we think about significant figures here and get really picky about it, there's actually 1 significant figure in this value right here. So if I was rounding this for significant figures, I'd probably round it to 0.2, but let's go ahead and call it 0.15 and call it good there. So let me do another couple of examples with you. It says, suppose 350 milliliters of 0.75 molar calcium chloride solution is added to excess amount of NaOCO3, so sodium carbonate. There should be a 2 there. How many grams of calcium carbonate will be recovered? So again, we're paying attention to state symbols, paying attention to the information that we're being given. This is an aqueous solution. It's saying there's 0.75 molar, and we've got 350 milliliters of it. And it's asking me for grams of this. So there's a few ways to approach this problem, but one way to do it would be, just like I did the last time, like in all stoichiometry, I need to find moles. And I can't use a mass. I can't look up the molar mass of calcium chloride on the periodic table. That doesn't help because this is a solution. It's mostly water. Instead, to find moles, I'm going to use the molarity equation. So I've got my molarity right there. It's 0.75. That I'm going to change to liters by moving a decimal over 3 times. So that's 0.350. And then I'm going to solve for moles. And just like in the last one, I'm going to solve for moles by multiplying both sides by 0.350. So just doing a little bit of algebra here. And so what I have determined based upon all of that is that I have 0.75 moles of calcium chloride. No, sorry about that. I was looking at the wrong thing. 0.75 times 0.350. I have, call it 0.263 moles. So from here, I already have moles of calcium chloride, so I'm just going to proceed with the stoichiometry. I already have moles, so I can go right to the mole ratio step. And in my experience, this is the part that people forget a lot, is they forget about the mole ratio in these type of problems. In this case, it's actually not going to matter because the mole ratio is 1 to 1 mathematically, but I still want to put that step in there so that I don't forget the times that the mole ratio does matter. And again, that's one of the biggest mistakes that I see students make in this is they'll forget about the mole ratio step. They'll do everything right, but they'll forget about the mole ratio. Here it's 1 to 1, so the mole stays the same. And now what I got to do is I got to change this back to a mass. And again, this part here is not any different than any stoichiometry that we've done so far. Now I am going to use the periodic table. This is a solid. I'm going to add up the mass of calcium carbonate. It's about 100.09. That's 1 calcium, 1 carbon, 3 oxygens. Add that all together. The mole goes on the bottom because what goes up must come down. And that's 100.09 grams. Squeeze that in there. So basically it's 0.263 times 100.09. call it 26.3, two significant figures here probably because of that, so we'll call it 26 grams. And that's our answer. Example 3, in your version of the workbook that you have, this is probably on the same page as all the other ones. It says excess zinc metal is added to 500 milliliters of a 0.25 copper 2 chloride solution. So copper 2 sulfate rather, that's this stuff right here. It's a solution, and it's saying how many grams of copper will be recovered. So eventually we're trying to find grams of a solid, and we're being given the volume and the concentration of a solution. And again, when that is the type of information you're being given, we can't use molar masses from the periodic table because it's a solution, it's mostly water. Instead, I'm going to use the molarity equation. I'm going to put in the molarity, which is 0.25. I'm going to solve for moles. This needs to be converted to liters by moving a decimal 3 times, so that's 0.500 liters. And solve for moles by multiplying both sides by 0.5. And so that is 0.125. So I have found moles, CuSO4, that's a U. I found moles. I found it in a little bit of a different way than we did in the stoichiometry problems to begin with, but still, like in all stoichiometry, we need to work with moles. The next thing we need to think about is the mole ratio. It is 1 to 1. So mathematically it doesn't change anything, but I want to think about it. I'm going to move this over a little bit. We want to make sure that we're thinking about it so for the times that it does matter. So 0.125 mole CuSO4. The mole ratio is 1 to 1. I always like to attach what I'm talking about to the mole unit. I'm trying to compare CuSO4 to copper. So I'm going to put 1 mole of CuSO4 down on the bottom, 1 mole of Cu on top. Now I want to go to a mass of Cu. Whenever we're going to a mass of Cu, now it's a solid, so I'm going to look up its mass on the periodic table. What goes up must come down, so I'm going to put 1 mole on top. I'm going to put copper's mass, which is 63.55 grams on top. Solve this out. Basically, it's 0.125 times 63.55. We get 7.94 grams of copper here. Now, again, if we're being picky with significant figures, this only has 1. So in theory, I should round that to 8 if I'm really going by the significant figures that are on the problem. So that's a couple examples. I think I'm going to do one more with you from the next page. So again, hopefully, if you were fairly solid in the stoichiometry concepts to begin with, it's really just this beginning step, how we're getting moles from the solution that's different. But other than that, all the concepts are still remaining the same. So the page following the ones that I've just been working on is this page. It says solution stoichiometry. There are a few selected problems. One I want to do is I want to do this one because that one is a little different than the ones that we've done before. Question 3 uses this question right here, so it uses the same chemical equation. I'm going to give myself a little bit more room here. So it says, consider the reaction above. Suppose I had 3 grams of copper. How many milliliters of a 2.0 molar solution of silver nitrate would be needed to completely react with the copper? So in this case, it's saying that 3 grams is solid. You got a solution. It's asking you how much of that do you need. And again, with a solution, you can't weigh it. You can't like put it on a balance and weigh it because you're weighing mostly water. Instead, you would measure its volume. And once again, the molarity formula can be our friend here to help us, except this time, we're going to use the molarity formula at the end. I know the molarity already, but notice I have 2 unknowns, so I can't use this equation already. I know the molarity already, but I don't know either one of these. But what I am going to do is I'm going to use stoichiometry to find this moles, and then I'll know the molarity, and then I can solve for liters. I'll show you what I mean. So 3 grams of copper. Copper is a solid, so I can just use its mass. I can work with its mass, and I can use its mass from the periodic table. So the periodic table tells me that copper has a mass of 63.45. And 63.55 rather. And so the mass from the periodic table is going to go on the bottom because what goes up must come down, and I got grams on top. That's the molar mass of copper. So just a normal gram to mole conversion here. And then, like in all stoichiometry, we want to think about the mole ratio. So I'm comparing this to this. It says I have 3 grams of copper. How many milliliters of the silver nitrate would I need? So the mole ratio is 2 to 1. So here is a spot where the mole ratio is going to matter. I got moles of copper on top, so I'm going to put on the bottom in the next one 2 moles of AgNO3. Now, in the stoichiometry problems we did at first, we would have kept going. We would have found a mass of AgNO3, but I'm going to stop right there because if I stop right here, grams cancel, moles of Cu cancel, I'll have moles of AgNO3, and then I can use this equation here and do some algebra. So I'm going to go 3 divided by 63.55 and times 2. So what that tells us is in this chemical reaction, I need, call it 0.944 mole of AgNO3. So to react all of that copper, I need 0.0994 moles of AgNO3. Now, looking at my little equation here, I have my molarity, which is 2. I have my moles from the stoichiometry, 0.099944 moles. And I have the unknown there in the denominator. So in the interest of time here, I'm going to remind you of a little bit of an algebra shortcut. The tempting or algebra mistake sometimes people make would be to multiply both sides by 0.0994. That's not going to work. There is a little bit of trick of algebra here that when you have an unknown in the denominator like this, you can switch these two things. So what that looks like is, oh, I moved that in. Whoops. I'm going to switch the unknown and the 2, so liters equals 0.0944 divided by 2. And so it ends up being about 0.472. Now that would be liters. And the question, I believe, asked me for milliliters. Yeah, so remember the liter to milliliter conversion is you move the decimal 3 times. When we were going from milliliters to liters, we move to the left. When we're going the other way around, we move to the right. So there's the decimal 1, 2, 3. And it would be 47.2 milliliters. So there's a few examples for you. Thanks so much for watching. Reach out with any questions that you have to myself. If you have a different teacher, you can reach out to that teacher. Thanks. Stay safe, and I hope you have a good day.